Laser sensors track plate thickness to 0.1 millimeter, while rollers apply thousands of tons of force. This process transforms 1,600 degrees Celsius molten iron into precision flat steel plates dozens of meters long. The real control happens in the hidden sensor network guiding every millimeter. Let's step inside the finishing mill. Steel plates form the backbone of bridges, ships, and pipelines. One mill produces over 2 million tons per year, each plate made within strict thermal and geometric limits. Strength, shape, and flatness depend on temperature uniformity, controlled reduction, and real-time sensor feedback. Every structure you walk across relies on these invisible tolerances. 5 systems define plate production: melting, continuous casting, reheating, roughing, finishing. Only one creates most defects, and it isn't the furnace. The first defect begins before the slab even forms. Ore and scrap melt in the electric arc furnace at approximately 1,600 degrees Celsius. Oxygen lances remove carbon. Lime binds sulfur and phosphorus into slag. Even trace impurities weaken entire plates. Clean chemistry determines downstream strength. But clean metal means nothing unless solidification happens under control. And that control starts when liquid steel meets a cold copper mold. The shell must solidify, but must not freeze too fast. Liquid steel enters a water-cooled copper mold. Surface metal solidifies in milliseconds. Rollers pull the slab down at 1 to 2 meters per minute. Spray cooling grows the shell to 20 to 30 centimeters thick. If withdrawal speed exceeds cooling rate, internal cracks. If cooling is uneven, surface tears. Continuous casting is controlled moving solidification, not simple cooling. The slab exists, but its temperature uniformity does not. And uneven temperature destroys the next stage instantly. A hot slab isn't enough. It must be evenly hot. The slab enters a tunnel furnace divided into independent zones. Burners raise temperature to approximately 1,200 degrees Celsius. Dozens of thermocouples monitor heat across the surface. If a cold spot appears, burners ramp automatically. If one region overheats, fuel drops instantly. Uneven heat creates soft spots and tears during rolling. Temperature uniformity enables controlled deformation. Now the slab is hot, but far too thick. Force alone can't reduce a 25-centimeter slab. Reduction must be gradual. Hydraulic cylinders exert thousands of tons of pressure. Multiple passes reduce thickness from 25 centimeters to 5 centimeters. Reduction rate protects grain structure. Too much strain in one pass, fractures. Roughing shapes mass distribution for final precision. The slab is thinner, but not yet flat or dimensionally accurate. That precision forms only inside the finishing mill. What happens when thickness drifts by 0.3 millimeters? Laser sensors scan every millimeter from above and below. Target tolerance, plus or minus 0.1 millimeter across plates up to 30 meters long. If drift occurs, hydraulic actuators adjust pressure in microseconds. Feedback loops run faster than human reaction time. Flatness and strength depend entirely on continuous correction. Process identity. Finishing isn't rolling. It is laser-guided deformation under high load. Perfect thickness is only part of stability. Cooling must preserve it. And cooling is where unwanted curvature forms. Cool the plate too fast, and it bends permanently. High-pressure water hits the plate at approximately 60 bar. Spray patterns balance edge and center cooling. Controlled cooling prevents thermal shock. Straightening rollers correct residual curvature. Ultrasonic sensors at 5 MHz scan for internal cracks. Cooling locks, geometry and internal integrity. Inspection confirms the entire thermal and mechanical history, from 1,600 degrees Celsius molten iron to precision flat steel plates, continuous casting forms, uniform slabs. Reheating removes thermal gradients. Roughing mills reduce thickness without fractures, and finishing mills, guided by laser sensors and microsecond feedback, deliver tolerances impossible by hand. What looks like brute force is actually a network of hidden controls working together. If you want the next breakdown, rail rolling, ship plate shaping, or quenched and tempered steel, drop your pick in the comments.